Hello everyone, welcome to Yebo Tutor Live. My name is James and I'll be your tutor for today. We will be looking at physics questions. So it's a good thing you guys highlighted the sections that you wanted us to look at today. So we will start with the electric circuits part, and then we'll also look into work, energy, and power as some of you have requested. So if we don't manage to do that today, we can also make sure that we cover somewhat that section in our coming streams. So the arrangement is we will be doing physics today, every Wednesday between 15:45 and 16:45. And Thursdays, we've set them aside for your mathematics. Then Friday, we'll introduce chemistry. So please tune in those 3 days. If ever there is anything that you feel we can address, someone indicated acids and bases, that will also be taken care of. So guys, if you have any specific need or anything that we can assist you with, please just indicate and we'll see if we can meet those expectations. Right, so the question that is showing already is a question on electricity. It's an electric circuit, so we'll look into that one first. I hope you guys are already connected. I'll just give you a few more minutes. I can see 2 viewers already. People are connected. That's good. So welcome, guys. You are all welcome, and we would want you to participate. Participation is very key for this program. You can chat with us via the chat box. You can type your comments. You can ask your questions there. You can even use our WhatsApp platform. We'll be able to address some questions from there and see how best we can help and assist you. So let's just maybe in the next minute we can start. Let's just be patient a little bit while others are still joining. Okay, so I think those of you that are connected, we can proceed. So what we have here, the question shown, I hope you guys can see it clearly. I'll try to maximize it as we have been doing all along so that you can read. Then I'll be removing it from the screen now and then. Okay, so this is the circuit diagram for our first question. So the first question reads calculate the value of resistor R if the total resistance of the circuit is 4.8 ohms. So we have a circuit diagram here. Consider the circuit diagram below. The internal resistance of the battery and any resistance in the wires can be ignored. So that makes the setup very simple. If we are not considering the internal resistance of that battery, which is shown here, right? That's the battery. And we have a resistor, which is 4 times R, another resistor, 2 times R, another resistor, a 3R, and the fourth resistor is just R. A voltmeter is connected across the 2R resistor. So that's basically what the diagram is showing there. And from the diagram, the first part to that diagram simply says calculate the value of the resistor R if the total resistance of the circuit is 4.8 ohms. Okay. So already you can see for this setup, here we have the 4R resistor across the source. Then we have the R, the 2R, and the 3R resistors in series with each other, but parallel to the 4R resistor. So we're gonna try and redraw this setup so that it looks simpler, right? So we have a battery. So this is question 12 on electric circuits. Okay. So with a battery, positive, negative, and there are a lot of cells in there. So that only shows that there are a number of cells that make it a battery. We have the battery connected like that. And across the battery first is this resistor, which is, it's simple to say that this is a parallel connection because it's up across the battery. In this case, because there is a junction there where the current branches. So take note that a terminal is a positive terminal, that's a negative terminal. Current gets to that point, it branches to go to this 4R resistor, and the other one goes to the 3R resistor, but we are allowed to put our 3R resistor there, because whatever point, whether we connect it to this point or that point or this corner or where we've put it, still that's the same point, because we have been told that the resistance in the wires is to be neglected. So there's negligible or a zero resistance from the conducting wires. So from the one side of the 3R resistor connects to this junction, which goes to 4R, but the other side connects to the 2R. So we can have our 2R resistor there, right? Then the left side of the 2R resistor connects to a 1R resistor, whose left side also connects back to the junction that comes from the 4R resistor. So already, let's label those points. Let's say this is point A and this is point B. You can see that point A connects to the 4R resistor and connects to the 3R resistor. After the 3R comes the 2R. From the 2R comes the R, and the R connects to B, joining again to the 4R resistor. So we have not really changed the orientation of that circuit. This is the same circuit, but in this orientation now, you can tell whether the combination is a series combination for which resistors or a parallel combination for which resistors. So what can you say about the combinations? Which resistors are in series and which resistors are in parallel? Okay, so you can see that the resistor R, the resistor 2R, and the resistor 3R are in series with each other. So we have a series combination of R, 2R, and 3R. So their total, so we have this series combination, R series, and their equivalent resistance is in parallel with the 4R resistance. So let's find RS first, or let's say our total resistance for the series part RS is equal to R plus 2R plus 3R. And this gives us 6R. So 6R is the equivalent resistance, or the resistor of the resistance of one resistor, which would represent or have the same resistance as the combination of the three. So that RS is 6R. And this 6R is parallel to the 4R. So total resistance, the total resistance for a parallel combination, it's 1 over the 4R plus 1 over 6R. And we are given the value of this resistance to be 4.8. This resistance is given as 4.8 ohms there. So calculate the value of resistor R if the total resistance of the circuit is 4.8 ohms. So given that this sum inverted is equal to 4.8 ohms. So for some of you, you know that if you just have two resistors in parallel, all you can do is just to say product over sum, which is to say 4R times 6R over 4R plus 6R. So this is the same as simplifying the fractions, 1 over 4R plus 1 over 6R, and inverting them. So you can use both methods and we can try them and see if they give us the same answer. So R total is equal to 4.8 ohms. And 6R times 4R times 6R gives us 24R squared over 10R equals to 4.8 ohms. So we remove this 1R and we have 24R equals to 4.8 times 10, which is 48 ohms. Divide by 24 both sides. That's 1 and that's 2. So the resistor R is 2.0 ohms. So this is the value of the resistor R. So if R is 2.0, it means the 2R resistor is twice that, which is 4 ohms. The 3R is thrice that, which is 6 ohms. The 4R is 4 times that, which is 8 ohms. So those are the values of all the resistors given in the circuit from that expression. I hope that is quite clear. It's quite an interesting question. So if we would use this method, what would we do? If for those that would not have recalled product over sum. So it's basically you being able to use your mathematical skills, right? 1 over 4R plus 1 over 6R, and we want to invert this. So we find the common denominator, which is 24R, and 4R into 24R is 6. 6R into 24R is plus 4. And we want that inverted. Then what we get there is 24R over 10 after inverting, and that is 2,4R, which we are told that the total is 4.8 according to the question, ohms. So this 2.4 will give us 2 ohms. So it's up to you to choose which method you think is simpler. And usually the simpler one will be the faster one for you. So you choose one that is simpler for you. So that's part 1. And the next part, is from part 12.2. Calculate the reading on the voltmeter if the current through the 4R resistor is 1.8 amps. So what would you do with this one? Part 12.2. What is the voltmeter reading? So you need to calculate that voltmeter reading. You are told that the current through the 4R resistor is 1.8 amps. So did we assign something to 1, 2, 3? So we can as well label them resistor 1, resistor 2, resistor 3, and resistor 4 from their values. So I4, the current through resistor 4, let's call it I4. We are given that value of current is 1.8 amps. So, you know, the interesting thing is once you have that current, you know from Kirchhoff's law, V equals to IR, right? I don't know how you remember this, but what is important is for you to just remember it. So with this triangle, basically what it means is if you are calculating V, let's shade that part for V. If you want to find V, then V comes from the product I times R. So if they're in the same line, they are multiplying I times R. If you want to find I, then we would close that part and we say I equals to, you find out that V is on top of R, so it's V over R. But it's all the mathematics anyway, are just rearranging that same equation and making, in this case, I the subject or R the subject. So if you want your R, in this case, what do? R is V over I. Because if you close out the part that has R, then V is above I. So R equals to V over I. So that's one way of remembering it, in case you forget. But as long as you don't forget any of these equations here, home and dry. Okay, so why did we bring into the picture this Ohm's law? We are given I through the 4 ohm through the 4R resistor, and we know R is 2 ohms. So which means the value of 4R, which means 4R is equal to 4R So we're saying 4R is equal to 4 times 2 ohms. Don't forget we said R is 2 ohms, which is 8 ohms. So the voltage across this resistor, V4 for the voltage across resistor number 4 is I 4 times resistor number 4. Let's call it R4 or times 4R. Yeah, 4R would do because we're given that as 4R times 4R. Where I is 1.8 amps and 4R is 8 ohms. So if you calculate 1.8 by 8, what do you get? What does 1.8 by 8 give you? So my calculation is giving me 14.4 volts. The voltage across the resistor is 14.4 volts. So what is this voltage? So we have current flowing, and this current is I. But when it gets here, it branches into I. We called it I4. And another part goes down there, which is I minus I4, right? Because the current is never created from nowhere, or like charge is never created nor destroyed. That's the principle of conservation of charge. So the amount of charges that reach point A are distributed such that some flow through the branch to 4R, some go through the branch to the other 3 resistors. So the same thing, the current will split into I4 and I minus I4. But we're told what I4 is. So I4 times the resistance there give us the potential difference between the either side of the resistor. So we call that potential difference VAB equals to 4R times I4, what we calculated. So the potential drop across points A and B is therefore equal to 14.4 as we found, 14.4 volts. This 14.4 volts is also therefore the potentials at the terminals because there is no resistance in the wires. So the current recombines there and goes back there so that the potential at B is the same as the potential at the negative terminal. The potential at A is the same as the potential at the positive terminal. So the potentials between A and B are the same as the potential drop, potential difference between the terminals of the supply source, voltage supply, which is our battery in this case. Okay, so now the reading on the voltmeter, we can find it if we know the current through the series combination, which means if we know this value. So how do you think we can find the value of the current through the other three resistors? That's very important. We want I minus I4. In other words, we need to find I. That way we can find the current that flows through these three resistors. So how do we know what I is? Don't forget where we started. We started by determining this. It's also, did we find here the total? Okay, well, anyway, we didn't even calculate. We are even told what the total resistance for the circuit is. So with the total resistance and the voltage from the circuit, we can find I. Okay, so I, there's our formula, it's now working. I is V over R. I equals to V, which is from the supply, which is equivalent also to V4. So I'll use V4 there for reference, over 4.8 ohms. Or let me not use a figure there and say over the total resistance, which is therefore equal to 14.4 volts over 4.8 ohms. So that should give us I. And this is 3 amps. So we have a current of 3 amps. And take note, the current through the 4 ohm resistor is 1.8. So the remaining current through the series part, we'll call it IS, because don't forget we said our total resistance there for this is S. So this is basically what we call IS, the current through the series resistors. The same current which passes through resistor number 3, this one, is the same current which will pass through resistor number 2 and also through resistor number 1 back to the junction. I hope we're together on that one. So IS is I minus I4, where I4 is 1.8 amps. So if I'm assigning these notations to say I4, IS, so that we know where it's coming from, where the current, which path the current is linking to, right? So you're free to just use any notation as long as you show it probably in your working and in your diagram, if you have a diagram. If you are given those quantities in your question, you just stick to the notation that is used in the given question. Okay, so IS is therefore 3. Let me just write first I minus I4, which is 3 amps minus 1.8 amps. That should be 1.2 amps. So the current through the other 3 resistors is 1.2 amps. Finally, the final stage. Don't forget, where are we headed? Or the goal is to find the voltage across the 2R resistor. So we know what the 2R resistor is, but we need to find also the current through that 2R resistor, so that we use V equals to IR to calculate the potential and hence the reading of the voltmeter. Okay, so across the 2RV for the 2R resistor is V2 equals to IS, the same current, times 2R. That is 1.2 times 2 times 2, which is 4. And V2 is therefore equal to 4.8 volts. V2 is therefore equal to 4.8 volts. I hope you are following, and I hope it's also making sense. So feel free to stop me or take me back to what you would have you wouldn't have understood clearly. Then we can also elaborate it further. Okay. So the next part, which is part 12.3 of the question, calculate the energy converted in resistor 4R in 2 minutes. What we want is energy. And we know electrical energy is given by V times I times time. So those formulae are very important to recall. So that energy is similar to this expression. Work and energy are equivalent. The work done by an electric source against a given resistance is given by V times I times change in time. So that's where we are getting that expression. So the time given, this is across the 4R resistor. So the voltage across the 4R resistor, we said V equals to 14.4 volts. We'll just list the given quantities, which will help us. I, so we say V4, I4. The current there, we say it is 1.8 amps. That one we're given. And the time is 2 minutes, but we have to convert 2 minutes to seconds, which is 2 times 60 seconds. So the rest is just history, right? Which means we already have our energy. E equals to 14.4 times 1.8 times 120. Can you calculate and tell us what you get? And what is the unit for energy? What is the unit for energy? That should be in joules. So it's 3.1 kilojoules or 3,110 joules. That should be the energy you get. For the energy across the resistor, the energy used in this circuit across the resistor 4R. So the next part, what does the next part say? How will the reading on the voltmeter be influenced? Right only, increase, decrease, or stay the same? If the 4R resistor is replaced with an ammeter. If the 4R resistor is replaced with an ammeter. Thank you, Viscolite has just commented, wonderful. So someone is following, guys. Someone is following what you are doing, and it's making sense to them. Thank you for that confirmation and for your wonderful comment. So the rest of you guys, where are you? What are you saying? It would be nice to hear from you. For those that I hope you are not facing connection challenges from where you are. I hope you are not facing any challenges with the connection. So now if the 4R resistor, where is our diagram? Should be there, right? So for this part, this 4R resistor is replaced with another instrument called an ammeter. We have an ammeter connected there. What change will that bring into the system? How will the reading on the voltmeter be influenced? What would you say? What would you say? So one thing you need to take note of is, what is the resistance of an ammeter like? Is the resistance of an ammeter greater than 8 ohms? Is it less than 8 ohms? Is it supposed to be even very high or very low? Ideally, what should be the resistance of an ammeter? So take note, an ammeter is a measuring instrument. It measures current and is connected in series with the part where the current is to be measured. So in this case, we are not placing the ammeter in that branch between A and B while the 4R resistor is still connected, because the ammeter would have recorded the 1.8 amps due to the presence of the 4R resistor. But what we're actually doing is removing completely the 4R resistor and placing an ammeter there. So it's like an ammeter is connected across, basically. It's like we've connected an ammeter across that circuit. And it would only give us probably the current that would flow maybe between A and B in that central part of the circuit, but it will not measure anything regarding the current passing through the 3R, 2R, and R. If we want to measure the current through the resistor 1, 2, and 3, then that would be a wrong way of connecting an ammeter, in other words. So take note of that. So the question is only a simple one where you have to say whether it increases. The reading on the voltmeter increases, decreases, or stays the same. So what would you say? I want your input, guys. I want your input. I want to hear what you think about this nice, simple question. So I was saying the ammeter, don't forget the ammeter is a measuring instrument. and is not supposed to affect the reading of current or introduce resistance into the circuit such that it affects the resistance of the line in which it is measuring current. It measures current at a point. Don't forget, current is charge passing through a point per unit time. So it has to measure the charges through that particular point of concern, right? In that particular line or branch in which the current is to be measured. So it measures current at a point. Is different from a voltmeter, which measures across 2 points. It measures potential difference. Hence, if you have a difference, then it means you need 2 points. One to the left, one to the right, or one on top, one below. Whichever is the case, you just need 2 points with the voltmeter. But for the current, you are measuring the current at a point, the charge passing through that point. Hence, you connect it in series. Okay. So what's your take? Decrease, increase, or stays the same? So taking note of the fact that the current meter, the ammeter, is a device or an instrument of very, very low or little resistance, it means introducing it into this branch between A and B is introducing a very small resistance or an easier path for the current to flow. So more current will flow through this path as compared to through the other path. So when current decreases there, it is definitely going to decrease what the voltmeter across the 2R resistor measures. So we have a voltmeter there. Across, this is what we mean by across, right? Just as the diagram was showing. So it's across 2 points on either side of the device whose voltage drop or potential difference we want to measure. So when we put an ammeter there, very low resistance, more current flows through the ammeter branch and less current through the other 3 series resistors. If less current flows there, then the voltage across this each of these resistors is also going to be affected. It's also going to decrease. So our answer there is decreases. Our answer there, we can say that the voltage decreases. We choose decrease. Explain the answer to the question. So that was the explanation. I'll just go over it again. The explanation is ammeter is a very low resistance device. So more current flows through the ammeter and less current will flow through the 2R resistor. And as less current flows through the 2R resistor, then the voltage drop across the 2R resistor will be lower. So the voltmeter will read a smaller value. So in other words, we can say the ammeter short circuits the resistors, or no current flows through the resistor 2R. So with a good ammeter, very low resistance will mean that all the current will simply flow through the ammeter branch and no current will flow through the 2R resistor. So basically that value on the voltmeter decreases. So it's like we have short-circuited. That's like short-circuiting. Okay, so let's look at this one is a continuation of electricity. It's the magnetism part. So we'll just look into this question too. A square induction coil with a side length 3 centimeters and 400 windings is placed perpendicularly in a uniform magnetic field and then rotated through an angle of 45 degrees in 0.08 seconds. An EMF of 7 volts is induced in the coil. So this is electromagnetic induction. The first part, which is 11.1, says state Faraday's law of electromagnetic induction in words. So the laws are very important for you to know the different laws and different principles. So Faraday's law of electromagnetic induction states that if allowed to flow, the magnitude of the induced EMF across the ends of a conductor is directly proportional to the rate of change of magnetic flux linkage with the conductor. So the magnitude of induced EMF, so this is 11.1. Magnitude of induced EMF is directly proportional to the rate of change. D over dt is rate of change of magnetic flux linkage, which is phi L with the conductor. So it's d phi dt. Flux linkage is represented by that expression. So this is the mathematical expression, which is expanded. In this case, the question says give it in words. So the magnitude of the induced EMF magnitude, because we are not giving the sign, the actual expression ends up as something like this. So there's that negative sign there because of maybe Lenz's law and conservation of energy. Right, so in this case, we are looking at the magnitude. Don't forget, it's also a key word to say the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linkage with the conductor. The magnitude of the induced EMF across the ends of a conductor is directly proportional to the rate of change of magnetic flux linkage with the conductor. Sorry, I totally forgot about that question. So this is the magnitude of the induced EMF. EMF is E, so its magnitude is directly proportional to the rate of change of magnetic flux linkage. So the magnetic flux linkage with the conductor is phi L, given by that symbol. You can just use phi, still okay, still acceptable. Magnetic flux. So 11.2 says calculate the change in the magnetic flux. Calculate the change in the magnetic flux. So most importantly, with this question, magnetic flux is just the number of field lines. So magnetic flux is just the number of field lines. And we have what we call a flux density, which is the number of field lines per unit area. So those are the different terms or terminologies that you would come across. But we're not talking of flux, we're just looking at the magnetic field lines, right? The magnetic field lines. And the more the field lines, if you can draw a stronger field, it has more field lines. A weaker field, it has weaker field lines, or the flux is less. The field lines are less. So the closer field lines are a strong field. The further separated field lines are a weaker field. So magnetic flux is just some indication of field strength, but it is represented, or it is the field lines themselves. So now we want the change in the magnetic flux. What is the change in the magnetic flux? So already I've given the expression which we need to use. It is this E equals to negative N divided T. Are we given E? I think so. It's the induced EMF 7 volts. So E equals to 7 volts. How many coils do we have? N is the number of coils. So in this case, it's a square induction coil. So that will represent only one. It's like 110. Oh, 400 windings. Okay. So it's a square induction coil with side length 30 centimeters and 400 windings. This is the number of turns. This is the number of turns. N equals to 400. No units, it's just number of windings. So the square there is just representing the shape of the windings. So it's 3 by 3 for this square induction coil with all those 400 windings. Then the time, 0.08 seconds dt. Any other information given? No other information required anyway. So what we want is d phi. So we're saying 7 equals to negative 400 times d phi over dt 0.08. And therefore d phi, the change in the flux, will be equal to 7 times 0.08 times 1 over 400. Which is negative 0.0014, and the units are Webers. The units for flux are Webers. So this is how we determine the change in the magnetic flux. This is the change in the magnetic flux. So the question that follows says, calculate the magnitude of the magnetic field. Calculate the magnitude of the magnetic field. So the magnetic field, you can use we can use a symbol B for it. That's the standard notation. So we have the change in flux. The change in flux, delta phi, should be equal to the field strength times the area, dot the area. So this is a dot product, and for a dot product, that means we take magnitude of B times magnitude of A times cos the swept angle. Let me call it delta theta. So we have B, which we don't know, but A, we're told that the sides are 3 centimeters. So that's 0.03 squared. That's the cross-sectional area. And it is the one that sweeps across the field lines. So cos the angle there swept is 45 degrees. The swept angle is 45 degrees during that time. And this should be equal to negative 0.0014. Such that B equals to negative 0.0014 over 0.03 squared times cos 45. So that's negative 0.0014 divided by 0.3 squared cos 45. Okay, I think this should be cos 45 minus cos 0, right? It should be like a delta cos theta there. I think cos theta final minus cos theta initial. I think that's how we should express that, which is cos 45 minus cos 0. Yeah, like that. So that part should be given that way. So it is the change in flux. Initially, when the angle is 45, you have got BA cos 45 finally. Initially, it's BA cos 0. So that was supposed to be from a factorization of that cos function. So that's the change in flux. It's initial flux from final flux, BA cos theta final minus BA cos theta initial. Okay. So B is 0,0014 over 0,03 squared times cos 45 minus cos 0. What does that give you? So B will be something in Tesla. Tesla is the unit for the magnetic field. And that's 5.3. That should give you 5.31 Tesla. Okay. So that's it for the magnetic field. The next part says, how will the induced EMF be affected? Write only increase, decrease, or stay the same. If the coil is now rotated through an angle of 45 degrees in 0,05 seconds. So we have changed the rate of change of flux linkage. In other words, for the same angle, but over a shorter space of time. Am I right? Is it a shorter? Yeah. So do we say increase, decrease, or stay the same? So if this change happens in a shorter space of time for the same angle, for the same number of field lines being cut, in other words, so if we cut more field lines over a shorter time, we've increased the rate. So when we increase the rate, according to our first definition, or the law, if the rate is faster, the magnitude of the induced EMF will also be faster. So the induced EMF will be greater. The magnitude of the induced EMF will be greater, sorry. So it will increase. Our choice there is to say increase. Then the explanation is that the rate of change of magnetic flux linkage is also increased by cutting the same number of field lines within a shorter space of time. So by cutting the same number of field lines within a shorter space of time, we increase the induced EMF, or the number of field lines the rate of cutting the field lines. So in other words, EMF is inversely proportional to the time. So you can see that EMF is inversely proportional to time. Right, I hope you are following, guys. I hope you guys are following, and this is making some sense to you. So we can proceed to the next part, which is about a bar magnet. The north pole of a bar magnet is pushed into a solenoid as shown in the sketch below. Which pole will be induced at point X, right, only, north, or south? So this is the question. The bar magnet, a north pole, being introduced into a solenoid with point X being at the side A of the coil, like that. The question is, which pole will be induced at point X, right, only, north, or south? So this should be very simple. You don't need to calculate anything or think hard about anything. What happens is when a north is brought into a solenoid like this, the solenoid responds or induces an EMF such as to create a pole which tries to oppose or to prevent the north pole from continuing to approach. So a north is coming. So to oppose this, we need to have a north at X so that it repels this incoming north. So the current that is induced inside there induces a north pole at X. So that's as simple as that. So the next question now says, in which current will the induced in which direction, sorry, will the induced current flow? Right, only from A to B or from B to A. So now we have a north pole there. In which direction can we say the current flows if there is a north pole there? So we have a coil like that. Okay, let me draw the cylinder first. Then the coil in blue. And okay, so there's A there, there's B there. Then we have induced, don't forget we are bringing a north. We are bringing a north there. So when we try and bring a north, point X also creates its own north. So if that is a north created, if we use the right-hand rule, right-hand grip rule or right-hand screw rule, where current flowing in a conductor has got a field around it, then which means for current, for a field that has a component towards the left inside the core of this solenoid, right? So in this case, for the solenoid, at the center of the solenoid, you have a field that you want to be a north, which is a source of the magnetic field, moving, in this case, to the left of the diagram that I've drawn. So that field will be induced by a current which is upward. A current should be upward in the section of the coil that is at A. So for a current which is upward induces a field which is outward at that point. Which color? There. Okay, so which means the current going in that direction tends to have a field which is like that. So that current is flowing basically from A, then right round the coil outwards through B. So each time it is to the near side of this solenoid, the current that is actually passing through all these parts is upward like that. So that's current. Then it comes out through there. So each time it is going there, it has got a component of the field inside the coil, which is towards the left end. That makes the left end a north. So that's how we determine the direction of that current. So from the other side, you can also do it on the other side where the current is going down. Then as the field goes around that section, it has a component at the center which is still towards our left. So still the fields will add up and have an effective or an overall field that makes a north at this end where we had X. So that's the direction of the current. It's from A to B. From A to B. Just like that. So guys, I think that's about it. We will leave some questions again for our next meeting. When we meet again, we'll be ready to work other questions that you guys would like us to look at. So for those of you that wanted to do work, energy and power, we're going to be doing that first thing in the coming session. So let's meet again tomorrow for mathematics. We'll be here same time, 3:45, live on Yebo Tutor. So from me, James, it was wonderful having you on the platform, and I wish you all the best with your studies. It's bye-bye for now.